I'd like to talk about the color image processing. As you remember in the last sessions, we talked about some noises, some filters that we can use in order to noise reduction. But we talked about the filters all in the grayscale image. But starting from this week, I would like to talk about the color image processing. But before I start to talk about the color image processing, you have to know that, as you remember, in the range of the lights, there was just this part that is the visible spectrum, because this is visual spectrum for human eyes. That this part is a combination of the different colors that start from violet in this area to red in this area. Yeah, it's and you know that, for example, this area and this area is not visible by the human eyes because it's the ultraviolet, this area, and this area is infrared, that's not visible with the human eyes. We talked about the shahab, talked about this range in the first session, and actually these areas start from approximately 400 nanometer to 700 nanometer. That we can see in this graph that starting from 400 to 700 is the range and they are in the nanometer. Do you know that in this area we have these colors, but as you know, the primary color in the computer vision or in the image processing are the blue, green, and red. And after that, with if we mix this color, we can generate other colors. But the primary colors are red, green, and blue, or blue, green, red. Now, if you are working in the MATLAB, you know that you have the RGB, R red, G green, and B. But if you are working with the OpenCV, you have blue, green, red. But you have to consider this, that the first matrix is the blue in the OpenCV, the second matrix is the green, and the third matrix is red. But in the MATLAB, it's the first matrix is red, the second is green, and the third matrix is blue. But we can say that in this range we have all colors that are visible by the human eyes. As I mentioned before, that the primary colors are red, green, and blue. And if we mix these colors, we can generate the secondary color, such as magenta, cyan, and yellow. That magenta is the mix of red and blue. Cyan is a mix of green and blue, and yellow is the mix of red and green. As you can see here, for example, if we assume that it's this circle is the green circle, this circle is the red circle, and this is the blue one, you can see that when we have the combination of the green and red in this area, we have yellow. When we mix the green and blue, we have cyan here, and when we mix the red and blue, we have magenta. And also if we mix all three primary colors, green, red and blue, we can find the white color that we can see here. And also we called these colors secondary colors, and also you can see when we mix the yellow and magenta, we can find the red color here, or we can generate the red color. When we mix the cyan and yellow, we can generate the green color, and when we mix the magenta and cyan, we can generate the blue. And when we mix all the three secondary colors, we can generate the black color in the middle of the circles. As you can see, for example, you know that we have when we have an image in the color, it means that we have three matrices. The first matrix I mentioned before is the red. One of them is green, and one of them is blue. But for example, you can see, for example, assume that the first pixel of the red matrix is 255, and the value of the green and the blue is equal to 0, but we don't consider here as a blue. It means that all the value of the blue matrix is equal to 0. We don't consider this. When we have the value of the 0 here, as a result, we have the when we add these two matrices together, we have the color of the red. But when we have the value of the 255 for the red matrix, we have the value of the 128 for the matrix of the green. We consider that the blue matrix is as the pixel of the 0. We can generate the orange color in the result image. It means that we have 255 here and 128 as a green. And also when we have the 255 and 255 for the red and green, we can generate the yellow color. We assume that the color in the blue are equal to 0, as you saw in the last slide, that when we just add the red and green, we can easily generate the yellow color. It was some fundamental about the colors that Pythagoras, most of you know about that. But in the image processing or video processing, we have some color models, or we can call it a color space. One of these models is RGB color model that use the primary colors such as red, green, and blue, and we can see here 3D Cartesian coordinates. It's based on the 3D Cartesian coordinate, and we can see here the simulation of this. For example, if we assume that this axis is red, this axis is green, and this axis is blue. It means that in each axis, for example, for the axis of the red, the value for the red is equal to 1, and the rest is equal to 0, and same for the blue, the last value is equal to 1. We normalized it to this value between the 0 and 1, but you know that in the image we have for example, in the 8-bit image we have the value of the 0 to 255. But for example, we normalize it to between 0 and 1, and then you can see that for example, in this axis we have the value of the 1 just for red, but before the normalization we know that this value is 255 for the axis of red, and also for the blue and green. And you know that we have the color cube here. We have the gray scale here that start from black. That's the point of 0 to byte. That's the point of the 1 on 1. And you can see here when R value is equal to 0, we have the color of black, and R value, when we have the R value is equal to 1, we have the color of white, and also you can see the gray scale from black to white. And also you can see, we know that this axis was red, this axis was green, and this axis was blue. And you know that when we go to this part of the cube, or you can see here, we have the color of yellow, same here, and also we have cyan when the green and the blue will come together to this part. And also magenta when we use the red axis and blue axis, then in this area we have magenta color with some definition for color. And you know that when we, as you remember, most of the monitor use the RGB system, RGB space, and actually you know that when we want to use the RGB model, we have to have image in the red, that image in the green, and that image in the blue. We call it RGB. Then we can mix the all matrices or all images to generate a RGB image. That's the combination of all color. If we remove some colors from the from our system, we know that we missed that color and the color that we can generate from that color. For example, in this image, you can see the value of the R is equal to 0. It means that we don't have any red color or the color that we can generate by using red in this image. We know that we have a blue and green here, and in the middle we have the colors that we can generate with these two colors. And also here we can see, if we remove the green color, similar to the previous one, we remove all the colors that we can generate with the green one, and also for this image that we kill or we remove all the blue colors. It means that in the matrix of the blue that's here, we put the 0 in all elements. That means that we don't have any blue color in our image. As you can see here, it's the Schausscat. We have the image in red, we have the image in green, and we have the image in blue. When we combine these images that are in the RGB, we can also generate a color image. As you can see here, that for example, we know that, for example, for this part, we don't have just the red or green or blue. It means that we have the combination of these values, but in a different way. It means that, for example, for this area, we know that it seems that it's close to the red. It seems that the weight value of the red image is more than the green and blue values. That we can easily generate some colors that are close to the red image. Or we can generate some color that is close to the red. And also you can see the gray scale that in grayscale of the image, it means that instead of the three matrices that we have, for example, red, green, and blue, we just have matrices in the 2 dimension that are values between 0 to 255, and it's just in the gray level that we talked about this type of image lots of before. And also you can see that actually when we see the exact image of the red, blue and green, it's not clear here, but we have something like this when we just have the red values on that image, green value and blue value on this image. Another color space or color model that we can use is CMY, cyan, magenta and yellow color that we call them the secondary color. It's another color model that some printers use this model, and you know that we can easily generate these colors from the RGB. How we can do it? It's you can see easily we can generate it from this equation, 1 minus R to generate the cyan, magenta, 1 minus this, and the 1 minus B to generate this image. And also you can see that, for example, for this color we have the cyan, magenta and yellow, similar to the RGB, and also we can show that the grayscale image of the this model. And this is another model that we can use. But you know that this although this model or this space used frequently in lots of applications, but as you know, they have some limitation. For example, if you take an image from, for example, this object, when the weather is shiny, we have, for example, blue here and some colors here. It's not so colorful, but for example here. But when the weather is rainy, and then we take the photo of this, the color is a little changed, and also when we have some limitation from the light, we can't get really the exact color that we want. For this problem, we can use HSI color model. That in this model we have hue, saturation, and intensity matrices instead of RGB matrices or C by M matrices that we have in other spaces. But we want to know that what is the hue matrices. We can see hue represent the purity of the color, pure red, yellow, green. It means that in the hue matrices we can say that we know that which color we have in our image in the hue matrices. In the saturation we can say that how much of this color we have in our image. For example, in the hue image we can easily say that we have red, green, blue, yellow and some colors in the image. And with saturation, for example, we can say that for this pixel we have, for example, 20% of the red, 10% of the green, 50% of the blue, and some other colors. We can say them in the saturation matrix. And The last one, that's intensity, is the actually is the gray level of the image that we can use. For example, if you use this image, this part of the image, you can easily represent the image in the grayscale that we can use. And we call, as I mentioned before, hue and saturation represent the color carrier. We call it chronon. These have the chronance information, and intensity that that have the luminance information of the image. You can see here, if we consider color as a circle, a triangle, and something like this, we the axis in hue is here. The axis of the hue is here. The angle between this vector and the saturation vector is exactly the value of the hue matrices. It means that we always have the hue matrices in degree or radian instead of the some values. And also, you know that for the intensity, we just have the gray level of the image. Also, you can see here, if we consider a circle, the hue is the angle between this vector that's start from red, and the saturation that we have here, and here this angle is the hue color. And you can easily know that if we put the zero instead of saturation and intensity, but we can ask you that what happens if we put the zero instead of the saturation and intensity in the HSI color model? We can easily say what's the color that it returns when we put zero instead of saturation and intensity. Do you know? You can easily see that. Where is exactly a scale of the vector of that we generate the hue of this? Know that in this color space, the primary vector is on the red. Then after that, we can generate the hue. For example, if we consider the saturation here, we have the 90 degree for the hue. It means that if we put zero instead of the saturation and intensity, we just have the red, because when we put zero, it means that saturation is here. We don't have any angle between this vector. It means we are just in this area, that we can just represent the red in the image. And also here there are different shapes for the image. It means that we just have red. And also you can see here in the shape the better view of the this color model. As you can see, we mentioned that the intensity is the gray level of the image in this color space or color model. Here we have the intensity of the zero. It means that we have the black color, and at the top you can see that we have the intensity of 1. That we have, it means that we have the white. You have to consider that we when we call it, when we are working with the value between 0 and 1, it means that we normalize the value from between 0 to 255 to 0 and 1. Then we have the black instead of 0 and white instead of white. And also you can see here the circle of this model. We can see here, similar to the previous one, the basic vector on the red, and we can easily find the hue of this, the value of the hue, or the angle of the hue, by finding the angle between this vector, that's the basic vector, and saturation vector, that is here. And you can see, for example, when the I is equal to 0.5, it means that when we are in the middle of this axis, we have color like this. You know that red is here, we have red here, cyan, for example, green, yellow in this area, blue, and magenta. Yeah, when we change the intensity of the image, it means that we don't change any, we don't change the value of the hue and saturation. We just change the intensity or gray level. For example, to 0.75, we can see that in the small area we have these colors, or it means that the value of the hue is a little less than here, and you can see in this shape the concept of the human saturation, hue, saturation, and intensity. And sometimes when we have the image in the color, we want to convert it to the HSI color space, we can easily just this equation to convert the image from RGB to HSI. As you know that I mentioned before, again we have to normalize it, the image between 0 and 1. It means that, for example, we have to divide the value to 255. For example, when we have the for the maximum value is 255, and we want to normalize it, we have to divide it by 255. Then we can find the value of the 0, and so on. We just after normalize the RGB values. It means that we have the modulus of the R, we have the modulus of the G, G is green and blue. We can say that if the blue modulus is less than, or the blue value at a certain pixel that we want to convert, we say that if the blue value is less than or equal to the green value, we can just easily put the angle that is between the basic vector and the saturation vector instead of the hue, that we call it theta. If the value of the B for the certain pixel that we want to use is greater than the G, we have to write 360 minus theta. How we can find the theta? For finding the theta, we can use this equation, sinus cosine inverse 1/2 R minus G plus R minus B. That's it means that the value of the red, value of the green, value of the blue, we have to put here over this. Then we can find the theta that we can put it for the, we can consider it for the hue matrices, and also you know that we have these conditions here. And also for the saturation, we have this equation 1 minus 3 over R plus G plus B, red, green, blue, multiple minimum value of the red, green, and blue, to find the saturation value for the certain pixel that we want to convert. And for intensity or I, we can easily say that 1/3 multiplied by red, green, the combination of the red, green, and blue value. We have to add all this value and over 3. We can easily find the hue value, saturation value, and I value from the RGB values for a certain pixel. And also sometimes we have the image in HSI color space, and we want to convert it to the RGB values. We can some equations to convert it, but we have to consider that when H is between 0 to 120 degree, you have to consider this. If you are working with MATLAB, it retains the value of the hue in radian. It means that if you want to use this equation, you have to change the radian, convert the radian to degree, and after that use this equation if you are working on MATLAB. But when the H, the value of the hue is between the 0 and 120 degree, we can use this equation for find the value of the blue here. It means that intensity multiplied by 1 minus saturation to find the value of the blue. To find the value of the R, we say that the intensity multiplied this 1 plus saturation cosine the H, that we know that the H is between 0 and 120. You have to consider this, that the H is in this range. If we want to find the value of the RGB from the HSI model. And also you know that for the value of the green, we can say that 1 minus R plus B, that we have these values from this equation here and this equation here, then we can easily find the value of the green. Also, when the H or the hue is between 120 degree between the 120 degree to 240 degree, first we have to find the H like this, H equal to H minus 120 degree. Then after that, similar to the previous equations, we can use this equation to find the H, but you have to consider this as a hue instead of the exact hue values. And you can find this. And also, if the value of the H or hue is between 240 and 360, we have to find the value of the hue that we can use here by this equation. The value of the hue minus 240 degree. Then we can use this value to convert the image from HSI model to RGB model. And also you have to notice that here to find the green we use this equation 1 minus R plus B, and for the value of the B we use this. But when the value of the hue is between 120 degree 220 degree, we have instead of the green by that equation, we have to find the blue by this equation. It means that we have to find the red and green, and after that blue by this equation. And for the next one, we can see that with this equation we have to find the R. It means that first we have to find the green by this. At the first situation we had, this equation was for the red, but here we have this for the green. and also this part for the B, and we can find the red with this equation. With hyperproperty, one of the question, for your final question is to convert the RGB to grayscale or grayscale, RGB to HSI or HSI to RGB, and with hyperproperty it's HSI to RGB, and you have to know this equation, and you have to know that first we have to see that H is between which degrees. And also you can see, for example, here we have the color circle in H. We have the color circle in the image, and you know that we have the color black. That because we have the bottom part of the axis, and also for grayscale, that you know that here we have the value of the white, means that when all the value you saw in I think in this okay, you remember that when the I or intensity is equal to 1, we have the value of we have the color of the white, and when is equal to 0, we have the value of we have the color of the black, and you can see when all are equal to 1, we have the white, and for the red part we have the black. After converting these matrices or these images to the RGB, we can find easily this image, that is the blue, green and red, or also when we convert it from the RGB, we can find these images. It was some color space that we used in the application, but it depends on the application that we want to use. For example, as you mentioned that when somewhere